Today we are going to discuss and cover the work energy theorem as it relates to biomechanics. The work energy theorem can be described as the distinctive relationship between work and energy. It is derived from Newton's second law, which states the acceleration of an object produced by a net force is directly proportional to the magnitude of the net force from the same direction. Also, it is inversely proportional to the mass of the object. This tells us that the net work done on an object to its displacement is equal to the change in kinetic energy. It can be expressed with the simple equation 1/2 times the mass times the velocity squared. The v initial and v final represent the speeds of the particle before and after the applied force. So work is the action that is performed on an object or system that transfers energy from one location to the other. It is evaluated as the force times the distance. Let's use three-time world and Olympic champion Simone Biles to help us understand this concept. In order for her to execute a proper vault, she must generate enough momentum to channel a sufficient amount of force to launch her above great heights. Using what we know, we can go ahead and calculate the amount of work it takes for Simone to do a successful vault with the weight of 104 pounds and a velocity of 4.4 meters per second. We'll convert the mass of Simone by dividing the 104 by 2.2 for a total of 47.27 kilograms. Next, we can set up the equation of kinetic energy to find her total work. The inputted values will give us an initial energy of 416.92 joules done by Simone. Since Simone is no longer moving and her velocity becomes zero, the final kinetic energy that is generated equals zero. We can now plug these two values back into the work energy equation, and since we are finding the change in kinetic energy, we'll use the absolute value to give us a total of 416.92 joules.